What's going on, everybody? This is Mr. Diamond. We're here to work out 3 example problems from Chapter 3 of Advanced Chemistry. These are our equilibrium problems involving Ka and Ksp. Now, I'm making the bold decision here to not work these problems out in advanced and to work them out my first time with you. Usually I work them out in advance ahead of time just to make sure that if I have a brain fart or anything like that, I don't get awkwardly stuck on what to do next or I do anything wrong. But I'm tired, so we're gonna just do this. We're gonna hammer this out and get it over with. So hopefully I don't make any mistakes, and if I do, I guess you'll not hear because this won't be the video you see. So our first example problem we're gonna do is the question says the Ka of hydrofluoric acid, which is HF, is 0.00071. What is the pH of 0.5? Get a pencil that actually works here. 0.50, sorry, 0.50, too many zeros, molar HF. Now, this is going to be an acid, which means it's ionizing because that acid is placed inside of water. So we have to go ahead and assume that our reaction is going to be HF plus H2O. HF is going to be aqueous because all of these acids are aqueous. I didn't mention that in the actual video, which is probably a little bit of an oversight on my part. But acids are aqueous because they have to be dissolved in water. But that acid can react with water to reversibly. Now, the reason this is reversible is because HF is not a strong acid, so it is reversible. At least I don't think it's actually on my list of strong acids. I guess I should, double check that real quick, but nope. Okay, good. Was on the list that I gave you. That would have been awkward. And then it's going to make hydronium, which is H3O plus, that is aqueous, and it's going to make F minus, that is also aqueous. Now going through and balancing, we've got 3 H's and F and an O, 3 H's and F and an O. So balanced, we are all good. We can go ahead and do our ice table. Now, it's saying that hydrochloric acid is going to have, we've got 0.500 molars. So 0.500, or sorry, just 10. 0.50 molar. I've been used to 3 sig fig questions. Water, we don't have a specific amount of water, but remember, water doesn't count because water is a liquid, and liquid means we get to ignore it for all these purposes. Now, we are technically going to use water, but it's also in an entire container of water, so the amount it's going to use is just not going to affect anything, and it doesn't affect the equilibrium, so we don't have to worry about it. We have no hydronium, and we have no fluorine. Technically, we would actually have hydronium in real life because the water would be forming it itself, but we're ignoring that. We're not going to worry about that. So now we can go through and, well, this is going to go down by an amount x. This is going to go up by an amount x, and this is going to go up by an amount x because the balanced version of this equation does not have any actual digits there, which means they're all ones. So we're going to have 0.50 minus x as our concentration of HF. We're ignoring water. And then we'll just have x and x. And now we can set all of these variables, and we can write our KEQ, or in this case, it's going to be our Ka expression. Our Ka is 0.007000. Did too many zeros, now I'm doing too few. 71. And then it's going to equal, we put products, so it's going to be H3O plus F minus HF, and again, we don't put water because even though in some of the problems you have been including it, it was talking about water vapor. This is liquid water, so liquid water is ignored. So we're going to go ahead and plug in our values that we know. We'll have x, and then we will have divided by 0.50 minus x. Okay, so from here, some of you who watched that shortcut video might go, well, can we ignore this loss? Can we get rid of this minus x that's right here because of the fact that we had that example where, you know, if HF or if your Ka or KEQ was really small in comparison to the concentration, you could ignore it. In this case, if we multiply this by 1,000, 1, 2, 3, we ended up with 0.71, which is actually more than 0.5. So no, we cannot ignore it. We are actually going to have to solve this out and do some algebra to get us there. So first things first, I'm going to rewrite it a little more clear. Also, I think my phone is going off. I hope you guys can't hear that vibrating. And then equals, we're going to simplify the top to x squared, and then our bottom would be 0.50 minus x. We're going to have to multiply this over to the other side. So 0.00071 times 0.5. We will get, I'll do my little equivalency sign, x squared equals 0.000355 minus 0.00071x. And now, well, we don't really have any way of eliminating anything or doing anything really nice to fix this, which unfortunately means we are going to have to do a quadratic equation for this one. So remember, we want to get that into the form ax squared plus bx plus c equals 0. I'm going to move these guys over to this side over here. So if I do that, I should end up with x squared, so nothing on that one. And then to get my bx, I'm going to add this piece over there. So it's going to be plus 0.00071x. And then minus, for our c, is going to be 0.00035. That equals 0. Negative b plus or minus the square root of b squared minus 4ac over 2a. At Jackson, they used to sing a little song. I think you guys said you don't do it, but it was sung to like the Pop Goes the Weasel. If you don't have like this memorized, don't worry. Well, first of all, you'll be allowed to access the internet because, you know, online tests, but also the fact that, you know, this will be on your test. I think is going to be on your test at least. If I forget that I intended it for it to be there, so don't feel bad having to look it up. So we'll go ahead and plug in the information that we know. I'm not going to write this out. I'm actually going to plug this in. Now, we're going to get two answers here. So I'm going to just set up that my plus gives me and then my minus gets me what it will get me of these two numbers. Now, the way I like to plug these in, the way that I think makes the most sense, is I like to plug it in once, all of it in one go, and then I can just enter it a second time and swap the plus to a minus and then see what I'm going to get. So I'm going to do parenthesis. Negative b is 0.00071. Plus the square root of 0.00071 squared minus, I don't think I really need it, but just to be on the safe side, we're going to do 4. A is 1, so I don't need that. So then I'm going to put 4 times negative 0.000355. Because again, this is supposed to be in plus. The fact that this is a minus here means this is actually a negative value, so 0.000355. Close parenthesis for that piece, close parentheses for inside of that, close parentheses for the whole top piece, divided by, and then I'm going to do parentheses just to be super sure that it's only dividing by the bottom. Well, in this case, it's actually a is just 1, so divided by, I guess I didn't actually need parentheses, so 2. So I get this value, and I get this value. Now, our positive is going to be 0.0184897, and our negative is will give us a negative 0.019199788. Now, between these two numbers, it should be pretty obvious what the correct answer is, because we can't have a negative value for our x. We can't have our HF be increasing and our H3O pluses be decreasing, especially because there's none of them here. You can't have this go even further. Like, we're pulling hydronium and fluorine from the ether to create more. Like, no, that doesn't work. So we're going to have to go with our positive value here. And normally we use this and we could say, okay, well, we've got our X and we're good. We know what our H3O plus is. However, we can't do that this time because of the fact that we have to go in and we actually have to plug in into a different equation. So going back to the question up at the top, it asks what is the pH of this. And pH, if you remember, is equal to the negative log of the concentration of H plus or of H3O plus. So what I actually have to do, because my H plus concentration, or H3O plus, again, they're interchangeable, just to be consistent on this problem, we'll swap it to H3O plus. Our H3O plus concentration equals X, which in this case is going to be, to the correct number of sig figs, 0.018. I think it's actually just 18, right? Yep, 0.18 molar. I apologize for that. Which makes sense because this is a number that's less than 1, which means reactants are favored, which means this is not actually going to ionize a whole lot. But now we're going to plug that into our negative log over here. So I'm going to go ahead and do negative log of 0.018 negative log of 0.018. We get a pH of 1.7447, which to the correct number of sig figs is 1.7, which is like really, really acidic, which is kind of crazy when you think about it. Like this acid, going into this, once you get to this point and you realize how little H3O plus it makes, your brain probably says, oh, that's not that bad. But this is actually a really large amount of H3O plus. This is a pretty intense amount of acid that's being produced, and it is actually going to probably severely damage you if you were to come into contact with this. So even though it doesn't seem like much, a 0.50 molar of hydrofluoric acid, because of its HF, or because its Ka is this low, that low amount makes a small amount of H3O plus, but that small amount of H3O plus is still more than enough to severely damage anyone who's actually coming into contact with it. Okay, I'm gonna go ahead and click on my screen just to make sure that, I mean, obviously you can't see that, but we're gonna move to the next problem. So I'm gonna flip over the page here, and now we're going to have the question of number 2. What is the pH of a 0.001 molar hydrochloric acid? Okay, this doesn't seem that bad. Now the weird part is we don't have a Ka or Keq or anything like that. But if we think about what's going to happen here, let's set up our equation. We've got HCl that's got to be aqueous. We know this is a strong acid. So when HCl reacts with liquid water, it is going to not form a double-headed arrow, which I hope I used the right arrow last time. Okay, I did. I bet I even made a big deal of the fact that I did that, and I still forgot 10 minutes later. So this is just a single-headed arrow. So we'll get H3O plus, it's aqueous, and this time we will get Cl minus, that is aqueous. And then when we balance it, 3 H's, 3 H's, 1 O, 1 Cl, 1 O, 1 Cl. Everything is just going to be a 1 here. Now this time, if we start with 0.1 or 0.001 molar of our HCl, as we go through our ice table, we're still going to do an ice table, but instead of it being X, it's just going to be the whole thing. And that means that because this is a 1-to-1 ratio, and if these guys started as zeros, we're just going to add 0.001 and 0.001, which means our H3O plus is 0.001, our Cl is 0.001, and our HCl is 0. And water we again ignore because it is a liquid. I apologize if that was too out of frame for most of that. But this is our equation set up right here, and there's no x's. There's nothing to solve for. Now, you're right. Going for the Ka or the Keq, we're going to end up with 0.001 times 0.001 divided by 0, which is not something that we can do in math. But that's why it doesn't give you a Ka or a Keq. All we have to do now is pH is equal to the negative log of our H3O plus. And in this case, that would be negative log of 0.001. Negative log of 0.001. We get a pH of 3. So going back to that other question that we were looking at here, this was 0.5 molar, and this was 0.001 molar. 0.5 molar is quite a bit more of an amount of this, and so it makes sense that it would end up being a lower amount of pH, because the lower the pH is, the more acidic that pH, or the more dangerous that pH is going to be. So this is 3. Technically, well, sig fig wise, this only has 1. So it makes sense that my answer is actually going to be a nice round number, because I only gave you 1 sig fig to worry about. So our pH in this case would be 3. Okay, now our final example is the one that's, again, not actually going to be that difficult. It's just a different approach to it. I actually should have enough space to do it on this same page right here. Hopefully I'm correct on that. So our question says solubility of, let me make sure that's on screen before I keep going, of calcium sulfate is 0.67 grams per liter. What is Ksp? So I mentioned this in the video a little bit, but our whole point here, so I get my new piece of lead that I hope is in this pencil. Okay, good. When these things react in water, what we're basically worried about here is we're saying that we're taking calcium sulfate, CaSO4, which I believe I have around here. Let me see if I can find it really quick. As you hear, cue all those cartoon noises of like cats meowing and like windows breaking as I throw stuff off. There it is. Okay, cool. If we check back here, sulfates, except those containing calcium, are soluble, which means calcium sulfate is actually insoluble. However, you can dissolve a teeny tiny amount of it. This is why I was kind of saying that these are more of guidelines over here. There's actually a lot of exceptions to these rules. And in this case, when we say something is soluble, usually we just mean you can get quite a bit of it in there. If something's slightly soluble, we don't really count that. And in this case, if you think of like an entire liter of water, like one big of those graduated cylinders, and you can fit less than a gram, or a big beaker, you can fit less than a gram of calcium sulfate in there dissolved before it stops, yeah, you're probably going to say that that's not soluble. So our solid calcium sulfate, if you put it in water, we're not actually going to include the water for this one. It's going to reversibly form, because what's actually going to happen is there will be an equilibrium between the ions and the calcium sulfate. So there's going to be an equilibrium happening here. And it'll turn into its components. So we have calcium, which is a 2+ charge that'll be aqueous, floating around in the liquid. And then we'll have our sulfate, which is our SO4 2- that is aqueous, that will be floating around in the liquid. Looking at balancing it, CaSO4, we're good. There doesn't need to be anything extra for balancing. Now, if we set up our ice table, we run into the problem that normally we've been using molarity, and we don't have a molarity. However, the question just tells you what the solubility in general is. It doesn't give you a specific amount. So you are allowed to assume whatever you want for that solubility. Like you could be saying, let's talk about 35 liters, or let's talk about 25 liters, or let's talk about 9,867,254 liters. But I will recommend, because I think it'll be easier, is we assume 1 liter. And if we do that, we now know that there is a total of 0.67 grams of calcium sulfate, of CaSO4. And if we know that there's that, let me get my periodic table out here, because we're gonna do some stoichiometry. I know that my calcium sulfate has a mass, a molar mass. I apologize if that had been off screen the whole time. I'm getting pretty bad at that. Okay, we've got 40.08, that's from the calcium. We've got, scroll over, 32.06 for the sulfur. plus 4 times 16 for the oxygen. So we got 136.14. So 136.14 grams of CaSO4 is 1 mole of CaSO4. So if we do 0.67 divided by our answer that we just got there, we will get 0.0049214 moles. And then from there, actually, I can leave that. If we assume 1 liter, our molarity of CaSO4 is 0.004921. Well, we'll just cut it off there, even though it's more sig figs than we actually need, divided by 1 liter, which is a molarity of 0.004921 molar. So now we know our amount we're starting with. We've got 0.004921. Okay, and then we're going to start with no dissolved calcium and no dissolved sulfate. Now that we have a molarity, it's literally the exact same process that we have been doing. So if we know hold on a second. Okay, that's what I get for trying to jump in to a problem without, double checking my work ahead of time. I'm glad I caught myself this early. Otherwise, we would have been we would have run into some problems. If you remember, we don't actually count an initial concentration of CaSO4. I honestly wish I could do this as a second video, but I am 20 minutes into a video and I really don't want to have to redo one. So we're just going to go ahead and power through this. So our CaSO4 is not going to actually be changing. It's going to be, there's so much of it that's going to be in there, but we do know that a certain amount of it is going to dissolve. And in fact, the amount of it that's going to dissolve is this amount right here. So that was where I was making my mistake a second ago. We know that this is how much can be dissolved. So whatever amount you start with, however big of a chunk of it is, if we're assuming 0.67 grams is the only amount, if we're assuming that we're just only dealing with 1 liter of liquid, we are going to lose our 0.004921. So this is the amount that we're going down by. These both have 1, so we're going to have to go up by that much. So up by 0.004921, and then up, again, these are going to start with 0, but plus 0.004921. Now I'm going to stop because I feel like every time I make one of these mistakes, I need to go back and re-explain. The question specifically states not how much you start with, which doesn't matter anyway, because again, molarity of solids, we don't care about that. That stays constant. I don't know if you heard that crash, by the way, but I'm okay. I'm alive. This is how much of it will dissolve. And if our question is how much will dissolve, well, whatever we start with, you're going to lose the stuff that's dissolved because it's no longer going to be solid. So that stuff that is dissolved is going to be subtracted from, well, the amount, again, it doesn't actually really matter how much we're starting. I think I accidentally bumped my pause button again. Man, this is just not going to be the video. Everything's falling apart. I don't actually know exactly where it got cut off. But the CaSO4, when it's dissolved, we don't care what the start is. We also don't really care what the end is, because at the end, again, it's just a solid CaSO4. Not only does that not factor into our equilibrium concentration, it's also a solid, so we can't even really judge what its molarity is going to be. But we know this is how many moles per liter we will lose, especially assuming we're at a 1 liter situation. And that means that if that's what's lost, that is how many of these pieces are going to be formed. If for every one of these that goes away, you'll make 1 Ca2 plus and 1 SO4 2 minus. So we just take 1 times that number. If this would have been 2, or if this would have been 3, we would have multiplied it by 2, multiplied it by 3, or whatever the situation needed. Or if this would have been multiplied by 2, and these would have been 1s, we would have divided it by 2. So this situation or this scenario works no matter what it is. But our point is that since this is how much was dissolved, that must be how much of this stuff was created, and that means our final concentrations are 0.004921, 0.004921. So for our KEQ, or in this case our KSP, because it's a solid, Well, we ignore the solids, which means the only things we have are our Ca2 plus, our SO4 2 minus, and then on the bottom there is nothing, so it's divided by 1, which is the same thing as there not being anything on bottom. So now all we have to do is 0.004921, multiply that by 0.004921. Now, I could square this, but just when I type this in my calculator, I am going to type it the long way. Let's clear that so you can hopefully see a little better. Actually, we'll move it right there. So 0.004921 times 0.004921, we get, I'm not going to do it in scientific notation, 0.000024216. We'll do the long version. And then double checking back in the question just to make sure I do the right number of sig figs. We have 0.67 and 25. 25 we don't really need, so just the 0.67. So our answer is going to be 0.000024, or just in case you want to do it, 2.4 times 10 to the negative fifth. And that is our KSP. I apologize for that error in there. I've made like 2 or 3 videos today in the past couple days, and I'm a little burnt out on talking and trying to work these through. That's the same reason I tried to do this without doing them ahead of time. My hands cramping from so much writing. But I hope that answers your question. I hope that makes sense. If you need another one of these examples worked out, please let me know, especially since I did this little mess up right here. You can also hop in the Zoom call that's going to be tomorrow or today. I don't know when exactly this is getting posted. I think on Monday with the notes video. But if you have questions, definitely hop in there. I will be happy to work out another example or to explain through the process in more detail, hopefully without errors that time. I hope you have a great rest of your day. I hope you have a great week, and I hope to see/hear from you soon.